So we want to calculate or we want to give you the formulas for between treatments estimate and within treatments estimate of population variance. So for the between treatments estimate of population variance, I am denoting it is MSTR, that is mean square due to treatments, is given as summation j runs from 1 to k. K is the number of treatments. Nj, so is the jth sample size for the jth treatment. Xj bar means the jth treatment mean minus overall mean whole square by k. K means the number of treatments minus 1. So the numerator of this formula is called SSTR, sum of squares due to treatments, and the denominator is the degrees of freedom associated with SSTR. Similarly, for within treatments estimate of population variance, I am calling it as MSE, mean square error. So which is given by summation j runs from 1 to k nj minus 1 into sj square by nt minus k. So j is running from 1 to k. K is the number of treatments. Nj is the sample size for the jth treatment minus 1 into sj square, sample variance for the jth treatment, by nt, total number of observations minus number of treatments. Numerator is called sum of squares due to error, and the denominator is the degrees of freedom associated with sum of squares due to errors. So if the null hypothesis is true and the ANOVA assumptions are valid, the sampling distribution of MSTR by MSC, of course, the ratio of two variances is an F distribution with MSTR degrees of freedom equal to K minus 1 and MSC degrees of freedom equal to NT minus K. If the means of the K populations are not equal, then the ratio will be inflated because MSTR, you know very well, overestimates sigma square. Hence, we will reject H0 if the resulting value of MSTR by MSC appears to be too large to have been selected at random from the appropriate F distribution. So too large, that's why better we use a upper tail test. So this is the thing. So if your test statistic is falling above F alpha, we reject H0 because it is an upper tail test. So how do you write the ANOVA table is very important. So the ANOVA table is first column source of variations. So we have treatments, error and total. So the next column is sum of squares. So you calculated SSTR, SSC and SST total. Degrees of freedom as usual K minus 1, NT minus K and NT minus 1. So now we calculate mean squares. So MSTR is SSTR by K minus 1 and MSC is SSC by NT minus K. Calculate F value as MSTR by MSC. Then finally calculate P. Degrees of freedom, I told you, right? Degrees of freedom long back in my first class only I told you. The number of independent observations. So for a okay, so SST generally the total sum of squares divided by its degrees of freedom NT minus 1 is the overall sample variance that would be obtained if we treated the entire set of observations as one data set. Total sum of squares, which means that for each observation subtract overall sample mean, square it and add it. That is known as total sum of squares. And the corresponding degrees of freedom is total number of observations minus 1. But from the previous table we can see that it is the addition of two sum of squares. One is sum of squares due to the treatments and the other one is sum of squares due to errors. So, ANOVA can be viewed as the process of partitioning the total sum of squares and the respective degrees of freedom into the corresponding sources, treatments and errors. Total sum of squares can be partitioned into sum of squares due to treatments and sum of squares due to errors. Similarly, their corresponding degrees of freedom can also be partitioned. So, for the equality of K population means using a completely randomized design, H0 is all population means are equal and HA is not all population means are equal. So, the test statistic is F equal to mean sum of squares due to treatments by mean sum of squares due to errors. So the p-value approach for rejection rule is reject H0 if p-value is less than or equal to alpha. And the critical value approach is reject H0 if the calculated F value is above the table value. Now, how do you check the table value? Alpha is given in the question and the degrees of freedom are, for the numerator, the degrees of freedom is k minus 1 and the denominator, the degrees of freedom are nt minus k. Nt is the total number of observations, k is the number of treatments. So I'm giving you a couple of examples too for the ANOVA. So testing for the equality of k population means I'm giving a completely randomized design. So AutoShine is considering marketing a long-lasting car wax. 3 different waxes have been developed. In order to test the durability of these waxes, 5 new cars were waxed with type 1, 5 with type 2 and 5 with type 3. Each car was then repeatedly run through an automatic car wash until the wax coating showed signs of deterioration. Now we understand each and every term for the given question. So in this question, the number of times each car went through the car wash before its wax deteriorated is shown on the next slide. AutoShine company must decide which wax to market. Are the 3 waxes equally effective? If this is the question, so we are talking about only one independent variable or factor known as car wax. So we have 3 different waxes. So that's why 3 different treatments, type 1, type 2 and type 3. And of course, if you want to take a sample, it consists of experimental units as cars. And the response variable for each experimental unit is the number of washes. So we have the data. So for first treatment or wax type 1, we have 5 observations. For wax type 2, we have 5 observations. And for wax type 3, we have 5 observations. And you know, one can calculate easily sample mean and sample variance for each sample. It's a routine calculation. Sample mean means number of observations by, total number of, sum of observations by total number of observations for each sample. Similarly, sample variance also you can calculate. Now, you have to write the null hypothesis and the alternative hypothesis. So, null hypothesis, all population means are equal, and alternative hypothesis is not all population means are equal. So, what is mu1? The mean number of washes for type 1 wax. Mean number of washes using type 2 wax is mu2, and mean number of washes using type 3 wax is mu3. Now you want to calculate the mean square between treatments and the mean square error. So here all sample sizes are same, the populations becomes very easy. First of all, you have to calculate overall sample mean, that is sum of all sample means by 3 because you have 3 treatments. Now we want to calculate sum of squares due to treatments. So sum of squares due to treatments is 5 because each sample size is 5. So 5 into 29 is the first treatment mean minus overall mean is 29.8 whole square. Plus second sample size is 5 into 30.4 is the second treatment mean minus overall sample mean is 29.8 whole square. Plus third sample size is 5 into 30 is the third treatment mean minus overall sample mean whole square. So sum of squares due to treatments is 5.2. If you want a mean sum of squares, then 5.2 by 3 is the number of treatments minus 1, that is 2.6. Now we have to calculate the mean square error. So mean square error means, you see first sample size is 5. So 5 minus 1 is 4 into first sample variance. Plus next 5 is the second sample size. So 5 minus 1 is 4 into second sample variance. Plus third sample size is 5. So 5 minus 1 is 4 into third sample variance. So it's coming out to be 33.2. Now mean square error is 33.2 by total number of observations is 15 minus number of treatments is 3, that is 2.77. So rejection rule is reject H0 if p value is less than or equal to 0.05. Critical value is reject H0 if f is above the table value. So table value, how do you calculate? Alpha is given, numerator degrees of freedom is 2 because 3 minus 1. Denominator degrees of freedom is 12 because 15 minus 3. So if you use a table, you got a number 3.89. So test statistic is F equal to MSTR by MSE, coming out to be 0.939. So if you go through the p-value, because you know how to calculate a p-value for a f, I told you long back, it should be greater than 0.10. Therefore, we cannot reject H0 because p-value less than or equal to 0.05 is our rejection rule. So therefore, there is insufficient evidence to conclude that the mean number of washes for the 3 wax types are not all the same because we are rejecting H0. So if you want to write the ANOVA table, so again, first column source of variation, treatments, error, total. Second column is sum of squares. Third column is degrees of freedom. Fourth column is mean squares. Fifth column is calculated F. And sixth column is p-value we got greater than 0.10. So if you take a second example for the same problem, so Janet Reed would like to know if there is any significant difference in the mean number of hours worked per week for the department managers at her 3 manufacturing plants in Buffalo, in Pittsburgh and Detroit. An F test will be conducted using alpha equal to 0.05. So a simple random sample of 5 managers from each of the 3 plants was taken and the number of hours worked by each manager in the previous week is shown on the next slide. So here anyhow the factor is the manufacturing plant. 3 different plants are there, that's why 3 treatments are Buffalo, Pittsburgh and Detroit. Anyhow the experimental units means the sample items. They are managers. And for each manager, the response variable is number of hours worked. So this is the data. So we have 3 treatments, and for each treatment we have a sample of size 5. Total 15 observations, 3 treatments. So for each treatment we can calculate sample mean, and also we can calculate sample variance. First sample mean 55, second sample mean 68, third sample mean 57. Similarly, sample variance for the first treatment is 26, second one is 26.5, and third one is 24.5. Now we want to write H naught. All population means are equal, and alternative hypothesis is not all population means are equal. So what is mu1? Mean yes, yes, yes. Yes. This is a completely randomized design. That's what we assumed. So in this problem, mu1 is mean number of hours worked per week by the managers at plant 1. Mu2 is the mean number of hours worked per week by the manager at plant. And mu3 is the mean number of hours worked per week by the manager at plant 3. So level of significance I have already specified alpha equal to 0.05. Now I am calculating test statistic. For test statistic I need MSTR and MSC. So mean square due to treatments, that is MSTR. So all sample sizes are equal. So overall sample mean is sum of individual treatment means. So treatment means are 55, 68 and 57 by number of treatments, that is 60. Now you want to calculate the sum of squares due to treatments. So the first sample size is 5. So 5 into 55 is the first treatment mean minus overall mean is 60 whole square. Plus second sample size 5 into 68 is the second treatment mean minus overall mean is 60 whole square. Plus third sample size is 5 into third treatment mean is 57 minus third overall mean is 60 whole square. So coming out to be 490. Now mean squares due to treatments is SSTR is coming out to be 490 by number of treatments is 3 minus 1, 2, that is 245. Now we will calculate the mean square due to error. So SSC, how do you calculate? First sample size is 5. So 5 minus 1, 4 into first sample variance. Plus second sample size is 5. 5 minus 1 is 4 into second sample variance. Plus third sample size is 5. 5 minus 1 in 4 into third sample variance. So coming out to be 308. So MSC is 308 by total number of observations 15 minus number of treatments 3, coming out to be 25.667. So therefore capital F is coming out to be MSTR by MSC, that is 9.55. So if you write the ANOVA table, so first column is source of variation, treatment, error, total. Sum of squares 490, 308, 790. Degrees of freedom for the first one it is number of treatments minus 1, 2. So next for error total number of observations minus treatments 12. Total is number of observations minus 1, 14. So mean squares we calculated coming out to be 245 and 25.667. So you calculate the F value as 245 by 25.667. So you can write the P value here. You know how to calculate the P value. I have written the exact value using a mathematical program, but you can write a value by using a table. So if you want to use a p-value approach, so the p-value is less than 0.05, so we reject H. If you want to use the critical value approach, you have to compare your calculated F value with the table value. How do you calculate table value? Table value you have to calculate for alpha equal to 0.05. Numerator degrees of freedom is 2 and denominator degrees of freedom is 12. So therefore, in critical value approach also, the calculated value is 9.55 and table value is 3.89. So calculated value is above the table value and it is a right tail test or upper tail test, we reject H. So in both the cases we have the same conclusion. So if rejecting H naught means we can conclude that the mean number of hours worked per week by department managers is not the same for all three plans. Okay. So this is the way we can deal with. Please remember, when I'm specifying that I'm using a completely randomized design, you please remember that we are assigning treatments to experimental units randomly. So in the second example, what happened? Somebody has asked me the same question. So we are assigning plans to manage. That's what the thing we are using here. So we are assigning plants Buffalo, Pittsburgh and Detroit to managers randomly. Means we are assigning treatments to experimental units randomly. Similarly, in the first example also, we did the same thing. So we have assigned type 1, type 2 and type 3 Carvaxes to cars. That's what assigned treatments to experimental units random. So that's what we are using a completely randomized design where we assign treatments to experimental units random. So I'll take a small break here. We have shown how analysis of variance can be used to test for the equality of K population means for a completely randomized experimental design. So ex- through experimental statistical study, we used completely randomized design and we tested for the equality of K population means. But at the same time, I told you not only in experimental statistical studies, we can also use ANOVA for observational studies. But I told you what is the main difference between both. So it is important to understand that ANOVA can also be used to test for the equality of three or more population means using the data obtained from an observational study. So in the previous concept, we have tested for the equality of three or more population means through an experimental study. That's completely randomized design. Now I'll give you an example of an observational study in which we are going to test the equality of three or more population means. So as an example, let us consider the situation at National Computer Products. So NCP manufactures printers and fax machines at plants located in Atlanta, Dallas, and Seattle. So we have three different plants. To measure how much employees at these plants know about quality management, a random sample of 6 employees was selected from each plant, and the employees selected were given a quality awareness examination. So please remember here we have collected a sample from each plant, whereas in experimental statistical studies, these three plants are called as three treatments, and we select 18 employees from all the three plants, and we assign plants to the workers. That's what the experimental statistical study using completely randomized design. But here what happened, we have selected 6 workers from each plant. So it's an observational study. So the examination scores for these 18 employees are shown in the following table. The sample means, sample variances, and sample standard deviations for each group are also provided. Managers want to use these data to test the hypothesis that the mean examination score is same for all the three plants. So obviously we define population 1 as all employees at the Atlanta plant, population 2 as all employees at the Dallas plant, and population 3 as all employees at the Seattle plant. So mu1 is the mean examination score for first population, that is the employees at the Atlanta plant. Mu2 is the mean examination score for population 2, that is the employees at the Dallas plant. And mu3 is the mean examination score for population 3, that is the employees at the Seattle. Although we will never know the actual values of mu1, mu2, and mu3, we want to use the sample results to test the following hypothesis. So null hypothesis is all population means are equal, and alternative hypothesis is not all population means are equal. So now let us compare this observational study with the experimental study. So note that the hypothesis test for the NCP observational study is exactly the same as the hypothesis test for the Chemitech experiment, because in both ways the hypothesis is same. Indeed, the same analysis of variance methodology we used to analyze the Chemitech experiment can also be used to analyze the data from the NCP observational study. So you can use the same type of ANOVA for both the things. Even though the same ANOVA methodology is used for the analysis, it is worth noting how the NCP observational statistical study differs from the Chemitech experimental statistical study. So you please understand that the present example is a best example for observational study, whereas the chemitech is a best example for experimental study. Yeah, in both the cases, null and alternative hypotheses are same, means same, the same way we define, and also you can apply the same analysis of variance technique for both the problems. But the principle involved in experimental statistical design and the principle involved in observational statistical design are different. In the experimental design, we applied a concept called completely randomized design. So now what are the drawbacks in observational statistical study over experimental? I'm just giving you. The individuals who conducted the NCP study had no control over how the plants were assigned to individual employees, because we have collected a sample from each plant. That is, the plants were already in the operation and a particular employee worked at one of the three plants. All that NCP could do was to select a random sample of 6 employees from each plant and administer the quality awareness examination. Just we picked it. We have not allotted plants to employees. Instead of that, at each plant we selected 6 people. So to be classified as an experimental study, so what to do? If you want to make NCP as an experimental study, so what to do? You have to assign plants to these workers. So to be classified as an experimental study, NCP would have had to be able to randomly select 18 employees and then assign the plants to each employee in a random fashion. Then only it becomes an experimental design. So this is the table where they selected 6 employees from plant A, 6 employees from plant 2, and 6 employees from plant 3. And their scores are given. So we can calculate the sample mean score, sample variance score, and sample standard deviation score. And you can even apply the same ANOVA here also. So that's why you can apply ANOVA for both experimental studies as well as observational studies. Yeah, because we use experimental design to control the selection process. Like here you see that in this observational study, NCP has no control over how the plants were assigned to individual employees. But whereas in experimental design, you have a control that you are assigning plants to workers in a random manner specified as completely randomized design. Yes. Right? So far we have discussed two important points. One, experimental statistical study, observational statistical study. In experimental statistical study, how to set up null and alternative hypothesis and how to use ANOVA. Similarly, in observational statistical study, how to set up null and alternative hypothesis and same ANOVA. And also we observed the main difference between observational and experimental. Now we'll move to the next concept called multiple comparison procedures. Suppose that analysis of variance has provided statistical evidence to reject the null hypothesis of equal population means. Like suppose analysis of variance told that all population means are not equal. Then Fisher's least significant difference LSD procedure can be used to determine where the differences occur. So in Fisher's least significant difference procedure, we can say that which mean is differing more significantly than the other. like what we did in the previous classes. So the null hypothesis is mu I and mu j are equal for a pair of means, and HA is mu I not equal to mu j. So in this case, the test statistic T is given by xi bar corresponds to the ith and xj bar is corresponds to zth by square root over MSC into 1 by Ni plus 1 by Ng. So rejection rule for p-value is reject H0 if p-value less than or equal to alpha. And critical value approach, so it is a two-tailed, so because we are checking not equal. So you have to calculate the T alpha by 2. T alpha by 2 is based on a T distribution with Nt minus k degrees of freedom, because we are using MSC in the denominator. So suppose if you want to use the Fisher's LSD procedure based on the test statistic itself only, then the same logic, maybe it's using a confidence interval approach. So if you take the same read example, I'm calculating the values. So for alpha equal to 0.05, Nt minus k means total number of observations minus 3, that is 12 degrees of freedom. And you can calculate the T table value for 12 degrees of freedom and alpha equal 0.05, T alpha by 2 is 2.17. So you just calculate Fisher's LSD value as T alpha by 2 into square root over MSC of 1 by Ni plus 1 by Nc. So LSD is coming out to be 6.98. So for plants 1 and 2, you will write H0 as mu1 equal to mu2 and HA as mu1 not equal to. So if you use the test statistic approach, it's just like a confidence interval. Reject H0 if mod x1 bar minus x2 bar is greater than or equal to 6.98. So mod x1 bar minus x2 bar is 13. So 13 is greater than or equal to 6.98. So you can say that the mean number of hours worked at plant 1 is not equal to the mean number of worked at plant 2. Similarly, you can try for 1 and 3, and similarly you got other way around. So what happened? There is no significant difference between the mean number of hours worked at plant 1 and the mean number of hours worked at plant. Similarly, if you do it for 2 and 3, you got again rejection. So that's why the mean number of hours worked at plant 2 is not equal to the mean number of worked at plant 3. So likewise, you can compare a pair of means also using these multiple comparison procedures. So in multiple comparison procedures, I'll repeat, in multiple comparison procedures, you can check where the significant difference is occurring. So if you take a pair of population means, then H0 is mu I equal to mu j and HA is mu I not equal to mu j. Of course, it is a two-tailed test. So the T becomes xi bar minus xj bar corresponds to ith and jth samples by square root over MSC into 1 by Ni plus 1 by Ng. If you then the p-value approach and critical value approach, you know. But if you want to use the confidence interval approach or based on the test statistic, in that way also you can write the hypothesis as mu I equal to mu j and mu I not equal to mu j. Then test statistic becomes xi bar minus xj bar, And you'll write reject H naught if mod xi bar minus xj bar is greater than or equal to LSD. So LSD from the previous slide is given by T alpha by 2 into square root over MSC into 1 by Ni plus 1 by H. So you can apply the same problem, read manufacturing problem to pairs. So we can start with plants 1 and 2. Then you can go for plants 1 and 3. And you can go for plants 2 and 3. That's it. Thank you. So far we have studied 3 points in our today's lecture. So one is experimental statistical study, and in particular using completely randomized design. 2 is observational statistical study, and for both the things we have established H0 and HA, and for both the methods we told you that you can use ANOVA for analysis. After that, we have discussed the LSD procedure. So what is the use of LSD procedure? Like, you can compare pairs of population means, and you can say where the significant difference occurs. So it can be done in 2 ways. You can use a t-test and you can give the output. So that's all for today, and if you have any queries, please let me know. Yeah, any queries about today's class? Do you have any queries? Any queries? Yeah. So thanks for today, and we'll come back with the remaining 2 designs, randomized block design and factorial design, in the next class, which completes the design of experiments chapter. Yeah. Thank you. Bye. Have a great day.